Well, so today we will be continuing with our discussions on the separated flow model. We have almost come to a last end. Till now what we have done, we have written down the mass, momentum as well as energy equations for the two phases taken separately, and then we have tried to combine them in different ways in order to obtain the mixture momentum equation. Then we have discussed regarding the condition of choking for the two fluid model rather. When the two phases are taken together, that means the condition of choking from the mixture momentum equation, and also the condition of choking when the two phases are considered separately. That means, we had considered the two phases separately. In this case, of course, to keep matters general, what we had tried to do is we had also incorporated the effects of change of phase. Okay. So, we had taken the two phases separately, and then we had tried to derive the momentum equations and the condition of choking for the two individual phases, and then we found that the choking of phase 1 or the choking of phase 2, it does not guarantee the compound choking of the two phases, because when two phases are flowing together, there is an additional parameter alpha, the void fraction, which can adjust itself and prevent compound choking, even though the two phases can be separately under choked flow conditions. So, therefore, we found that in order to estimate the choking, the compound choking from the two fluid model, as it is said, we would have to eliminate alpha from the two equations, and accordingly we found out an expression of the condition of choking, where we found out that for choking to occur, one of the fluids has to be in the subsonic condition, while the other is in the supersonic condition. And of course, after that we try to incorporate the effects of flashing and things like that. So, the more or less we have completed the two fluid model. The only thing which is remaining at present is, if you remember the basic equation which we had derived for the two fluid model, the equation which is there in this particular PPT, you can see this was the more or less the general equation, and we found out that if you consider this equation, then in this equation, in order to find out rho Tp, you need to have an estimate of the void fraction. Okay? And the other thing was the frictional shear or the frictional pressure gradient, which has been represented as Fw. It comprises of the frictional pressure gradient which phase 1 has with the wall as well as which phase 2 has with the wall. So, it can be written down in something of this sort, the two phase wall shear stress S by A, it can be written down in this particular form, so that we can find out that finally the combined momentum equation for the one dimensional approach can be written down in this particular form, and we find that in order to evaluate pressure gradient, we need to have an estimate of the frictional pressure gradient as well as alpha. Okay. So, therefore, if you observe this particular equation very closely, we find that it resembles the one dimensional homogeneous flow model which we have already done. Okay. The only variable being that along with the frictional pressure gradient which has to be considered, the alpha is also a variable in this particular case. Okay. So, therefore, we find that just by relaxing, what is so very different from this equation as compared to the homogeneous flow model expression that we had derived. If you remember the homogeneous flow expression, you will find that we had one frictional pressure gradient term, we had a gravitational pressure, sorry, this part is wrong, this part definitely it is wrong. So, I will try to, let me see if I can do it, otherwise just keep in mind that this is a mistake, this cos theta should not have been there, anyhow we will be correcting it. So, therefore, we find that there is a frictional pressure gradient, we find that there is a gravitational pressure gradient, and if you remember the homogeneous flow model, you will find that in this expression we had d dz of Gu or 1 by a d dz of Wu, because in that case we did not differentiate between the velocities of the two phases. We assume that the two phases under no slip conditions, they are flowing as a pseudo mixture with uniform velocity, due to which we had written down u1 equals to u2 equals to j. So, what is the only assumption of the homogeneous flow model that we have relaxed in this particular case? We assume the two phases to flow at two different velocities. Okay? Otherwise, they cannot flow in the separated flow condition because the densities are naturally different. Okay? So, therefore, in order to find out the frictional pressure gradient, what we basically did, or usually the approach is, we usually try to develop different types of empirical approach based on the condition, the basic assumptions, if we can mention the basic assumptions. If you find that most of the assumptions, they will be similar to the homogeneous flow model, except the first assumption. There we had set constant and equal velocities for the two phases. Now, remember one thing, these empirical approaches were initially developed for gas and liquid or vapor liquid phases. Therefore, most of their terminologies will be dealing with vapor liquid or gas liquid. The subscripts, instead of 1 and 2, usually we will be putting the subscripts as capital G and capital L, okay, or capital V and capital L. But in your, whenever you are using them, you can use either 1, 2. Phase 1 is naturally the heavier phase, since it is a separated flow model. Phase 2 is the lighter phase. In the beginning, when we were discussing about the nomenclatures, I had already mentioned phase 2 is the dispersed phase, phase 1 is the continuous phase. When both the phases are continuous, then phase 2 is the lighter phase, phase 1 is the heavier phase. Okay. So, therefore, in order to keep parity with whatever we have been doing till now, you can use subscripts 1 and 2 to denote the heavier and the lighter phase, or in other words, since most of them have been derived for gas liquid as well as vapor liquid cases, you can use subscripts L and G for this case as well. Okay. So, we find that the first assumption for the homogeneous flow model, the first assumption was equal velocities, constant and equal velocities for the gas and liquid phases. Okay. So, this has been modified in this particular case. It is constant, but not necessarily, definitely not equal velocities. If it is equal, then it reduces to the homogeneous flow model. So, therefore, constant, but not necessarily equal velocities for the two phases. The other thing was there as well, attainment of thermodynamic equilibrium between the phases. If you remember, there I had said attainment of hydrodynamic and thermodynamic equilibrium. So, in this case, it is attainment of thermodynamic equilibrium between the two phases. Okay. And based on this, what we usually try to do, usually what happens when we do not know anything, we go for some empirical approach. How we take up? We suggest some relationships which have been obtained by curve fitting a large data bank obtained from experiments. So, we try to curve fit those particular data bank, and then we try to obtain an empirical relationship when nothing is available. Now, how this empirical relationship is developed? Naturally, we will try to develop it in terms of something which we already know. Now, the conventional practice which I had already mentioned when I was teaching you the homogeneous flow model, usually we try to express the empirical correlationships in two ways. Either it can be in terms of friction factor or in terms of two-phase multiplier. That I had already mentioned. We can either, in homogeneous flow model, we tried to express it in terms of FTP. If you remember, where we had said that FTP is a function of two-phase Reynolds number RETP. But there also it was not very convenient, because we had to incorporate mu Tp. Now, mu Tp was logical when the two phases were intimately mixed, but when the two phases are flowing separately, naturally in that case incorporating a two-phase viscosity is not at all a logical thing. So, what we have to do in this particular cases, so the only option is to suggest empirical correlations in terms of two-phase multipliers. Now, what are these multipliers that we had already discussed before? The two-phase multipliers, they express the frictional pressure gradient for the two-phase flow as a ratio of the single phase pressure gradient which would occur if either the gas or the liquid would be flowing alone in the pipe. So, as I had already discussed, there were 4 different definitions of the two-phase multipliers that can be suggested. When it is either the liquid of the pipe which will be flowing alone now, the gas which will be flowing alone now, the entire mixture flowing as liquid, the entire mixture flowing as gas. Okay. Accordingly, we had defined 4 frictional multipliers. You must be remembering these things. The first one was phi square LO. Remember, these subscripts usually we use them as capital. Okay. Then there was phi square GO, usually we use them in terms of liquid. Okay. So, this is minus dP dz divided by minus dP dz when the liquid, the entire mixture flows as liquid. Okay. Then this was just from analogy, this was as a ratio of the entire mixture flowing as gas. Okay. And then we had phi L square, where the liquid portion of the mixture, it is expressed as a ratio of the liquid portion of the mixture flowing alone in the pipe, and phi G square, which is the gas portion of the mixture flowing alone in the pipe. So, these were the 4 definitions that we had already given. Now, at this particular juncture, I would like to mention that usually these correlations, if you see my slide, it is already written there. Usually in this particular correlations, they are expressed in terms of phi L square and phi G square. Okay. So, it can be the basic assumptions on the basis of which the empirical relationships to find out the frictional pressure gradient are based on the 3 assumptions which are given here: constant but not necessarily equal velocities for gas and liquid phases, attainment of thermodynamic equilibrium between the phases, use of empirical correlations or simplified concepts to relate 2-phase multiplier as well as void fraction alpha to independent variables of flow. Okay. So, first we would like to relate the 2-phase multiplier, and then naturally if the 2-phase multiplier is related with that particular parameter, alpha should also be related. So, accordingly we will find out empirical correlations to relate 2-phase multiplier as well as the void fraction to independent variables of flow. Okay. Once this can be done, we find out that Fw can also, or the frictional pressure gradient can also be calculated, and your once alpha is known, your rho Tp can also be calculated, u1 u2 can also be calculated. So, therefore, the frictional pressure gradient can be obtained from this particular equation. Now, here I would like to mention that out of the 4 definitions of phi square which I have already written down just now, the 4 definitions which we have written down just now, out of that usually we adopt phi L square and phi G square, rather we correlate phi L square and phi G square for our purpose. We do not use phi, usually this phi L square and phi G square, they are used for when we encounter change of phases or when there is boiling, condensation, etc. When a single phase, say liquid, a saturated liquid or a saturated vapor is entering and change of phase occurs. Under that condition, if we take phi L square, phi G square, then it is much more convenient, because liquid or the vapor was flowing alone in the tube at the entry condition. But under normal circumstances, when we are developing the 2-phase multiplier correlations from the separated flow model, we assume from the very beginning both the phases are present. In that case, we have found that it is much more convenient to use phi L square and phi G square. Why is it more convenient? Because we will soon see that these 2 multipliers, they conform to certain limiting conditions which are not obeyed by phi square LO and phi square GO. Just because of that, we would like to prefer, or we would like to correlate phi L square and phi G square. Now, what are those limiting conditions? Let us see what are those limiting conditions. Now, for no gas flow, what will you get? Let me write down the definitions once more. Phi L square minus dP dz by minus dP dz liquid, phi g square is minus dp dz by minus dp dz gas. Now, tell me, for no gas flow, what will you get? What should be the value of phi L square and phi g square for no gas flow? What is 1 by phi L square equals to for that particular case? Only for no gas flow means only liquid is flowing. So, 1 by phi L square will be equal to, since only liquid is flowing. So, therefore, the two phase, sorry, these are all two phase pressure gradient. Okay. Here also I would like to make the changes, they are all two phase pressure gradient. I am very sorry. In case I miss it, just remember that they are all two phase pressure gradient. Okay. Now, you tell me what is the, when there is no gas flow, then naturally it is only liquid which is flowing through the pipe, is not it? So, therefore, under that condition phi L square becomes, or 1 by phi L square, phi I am using 1 by phi L square, you will understand, 1 by phi L square becomes 1.0. And what about 1 by phi g square? 0. Just for this I have defined them not as phi L square phi g square, but as 1 by phi L square and 1 by phi g square. Similarly, for no liquid flow, I also have them in my presentation. You can see the PPT which I have prepared. Here also for no liquid flow, no, so naturally what do you have? It is 1 by phi g square equals to 1 and 1 by phi L square equals to 1. Remember one thing, these are the limiting conditions which phi LO square and phi GO square would not have conformed to, is not it. So, therefore, when there was no liquid flow also, we would find that there would be some value of phi square LO, is not it, because what do we assume there? We assume that the entire mixture is flowing as liquid. So, when there is no gas flow also, the liquid flow would be there. Do you understand? So, such limiting conditions would not have been, or they would not have been subscribed by your phi square LO and phi square GO. Another limiting condition that is also obeyed by this, that limiting condition is the relationships between phi L square and phi g square at the critical point. All of you know what is the critical point? What happens at the critical point? Louder? The two phases cannot be distinguished at the critical point, that is the definition. Why does that happen? Rho 1 becomes equal to rho 2, mu 1 becomes equal to mu 2, and therefore, all the properties of the two phases become identical. Now, let us see how the relationship between phi L square and phi g square, they change at the critical point. Now, what is the basic definition of these two? So, here I will just complete it. This was 1 by phi L square equals to 0 and this was 1 by phi g square equals to 1. Anyhow, now at the critical point, what do you get? We find that at the critical point, or rather let us first find out the expression and then we will be substituting the expressions for the critical point. Okay. So, what is the definition of phi L square? It is as I have just now written down, it is the two phase pressure drop divided by the pressure drop when the liquid flows alone in the pipe. Okay. Now, if we substitute the basic definition, there is one more thing, sorry, which I had forgotten to mention. Now, these things or these empirical approach, this has been derived under certain conditions. These conditions, if you observe, these conditions are, these particular derivations or empirical approaches have been derived under conditions of no phase change, no acceleration pressure drop and negligible body force effects. That means, for a horizontal pipe under isothermal two component flows. Do you agree with me? It has to be a horizontal pipe under two component isothermal flow. Yes or no? So, if that is the case, then what do we find? your g cos theta, this term it cancels out, okay. There is no acceleration pressure drop, this term it cancels out, and therefore, under that condition your pressure gradient is nothing, it comprises only of the frictional pressure drop, is not it. So, therefore, we find that these particular correlations, they had been, most of the empirical approaches, they have been developed under conditions of no phase change, no acceleration pressure drop and negligible body force effects, under which we can write, under this condition we can write it down as minus dp dz two phase. This comprises of minus dp dz frictional component of the two phase, right. So, this can be written, and later on some modifications were there in order to incorporate effects when body force effects and acceleration pressure gradients become important, but naturally the more important they become, the less accurate these correlations become. Okay. So, under this particular condition the correlations were developed. So, if this is applicable, then in that case your phi L square, it becomes, here only I will write down, this is frictional pressure gradient of two phase, and this also becomes frictional pressure gradient of the liquid phase, is not it. So, therefore, by definition, what is this? By definition, this becomes 2 FTP, correct me if I am writing anything wrong, g square Tp Vtp by d, yes or no, divided by 2 FL g square Tp into 1 minus x square, is not it. This is the amount of liquid which is there, g into 1 minus x is the amount of liquid which is contained in the two phase mixture, right. This will be VL or V1, whatever you want, and this will be divided by d. Do you agree with what I have written, yes or no? Fine. Same, or in other words, here in the same way your minus dp dz frictional for the gas phase, that also can be expressed in a similar way. Okay. So, therefore, we find what is the expression of phi L square when these particular the assumptions which I have written down in my transparency, under these particular assumptions, what is the expression of phi L, then we find that these cancels out, these cancel out, d cancels out. So, therefore, this reduces to FTP Vtp by FL 1 minus x square VL, yes or no? Is this portion clear to all of you? Fine. Achha. Now, at the critical point, what do you get? At critical point, what do you get? Rho 1 equals to rho 2 or V1 equals to V2, is not it? So, therefore, VL equals to Vg equals to Vtp, yes or no? So, therefore, these two also they cancel out. Do you get this? Right. So, therefore, this becomes FTP by FL into 1 minus x whole square. Now, what is the expression of FTP? Can you tell me? This FTP, this is a function of Reynolds number. Okay. So, therefore, this becomes a function, or this is k mu Tp by dg whole to the power minus n. You agree? Achha, same way FL, this is equal to k mu L by, or in okay fine, we can write it in this dg into 1 minus x whole to the power minus n, yes or no? So, therefore, here we can write it down as this is equal to, I have to shift to the next page, this is equal to phi L square, this is equal to mu Tp by dg whole to the power minus n divided by mu L by dg into 1 minus x whole to the power minus n 1 minus x square. This is the relationship which we get. Again at the critical point, for we know mu 1 equals to mu 2 equals to mu Tp. So, therefore, at critical point what do we get? Mu Tp's, they mu 2 mu's cancel out, dg they also cancel out. Okay, fine. So, what is the final thing that you get for this particular case? What is the final expression that you get? It is 1 minus x whole to the power n by 1 minus x square. This is equal to phi L square. Yes or no? Just check up whether I am doing things correctly or not. Okay. Similarly, phi g square, what will you get? For phi g square, it is going to be x to the power n by x square will be equal to phi g square. So, we find that phi L, the relationship between minus, what happened? It is all right only, is not it? Oh, sorry, now here also I made this mistake, is not it? Minus n, sorry, very sorry. Fine. Okay, in other words, you can just write it down as minus n plus 2. Okay. Acha. So, therefore, what do we find? That the relationship between phi L square and phi g square, they at the critical point, they will depend on whether the flow is laminar or turbulent. Yes or no? Okay? Because we find that both at the critical point, the phi L square, it is a function of x and n, is not it? And in this particular case also it is a function of x and n. So, therefore, the relationship between phi L square and phi g square at the critical point, that will depend upon whether the flow is laminar or whether it is turbulent. If it is laminar, then what do we get? For laminar flow, n equals to, for laminar flow n equal to 1, very correct. So, therefore, phi L square will be equal to, come on, phi L square, it is going to be 1 minus x 1 minus x only whole to the power minus 1. Check it up, check it up. How can it be minus 3? Just check it. N is 1. So, therefore, this is 1 by phi L square if I make it, then in that case, okay, let me make it 1 by phi L square, then this is going to be 2, just then probably I have made a, just a minute, let me just check up, maybe somewhere there is a mistake which I have made. FL by FTP, what did I get? There probably I have made a mistake. So, suppose I start from the very beginning for the laminar flow, then this becomes minus 1. Suppose for laminar flow, if I start from the very beginning, okay. So, phi L square becomes, this is minus 1, this is minus 1, and then in that case we get f by FTP. In this particular case, what do we get? FL by FTP, this is equal to 1 by 1 minus x, very correct. Okay. And in the same way, we will get, just a minute, where FL by FTP, next page. Oh, here na? No, here only I had made a mistake. Sorry, here only, very sorry, here only I made a mistake, just a minute. This FTP equals to K RE to the power minus n. Okay, so I have written 1 by RE, there only I had made a mistake. This is 1 by RE I have already written, so therefore it has to be plus. Here only I had, none of you pointed out the mistake, that is the thing. From here itself I had started making the mistakes. Okay. So, therefore, this has to be plus n, this has to be plus n. Is it correct? Because the relationship is f equals to k r e to the power, I had already written 1 by r e in this particular case. There actually I made a mistake. I am very sorry about it. So, very sorry, very sorry. Now it is all right, is not it? Very sorry. So, therefore, phi L square, this is equal to 1 minus x n minus 2, fine, or in other words 1 by phi L square, this is going to be 1 by 1 minus x whole to the power n minus 2, correct, and phi g square will be x to the power n minus 2, very true, and I have just made it the denominator. Achha, and this one is going to be 1 by phi. I am writing it as 1 because these two relationships will come out in a very straightforward manner, fine. Now, for laminar flow, what do you get? For laminar flow, your n equal to 1, is not it? So, when you get n equal to 1, then in that case what do you get? One by phi L square. So, therefore, you just do it and then you see how are you getting plus, you added 1 by phi L square plus 1 by phi g square. This what are you getting? This will become 1 minus x plus x equal to 1 for laminar flow, correct. For turbulent flow, suppose you, this is for laminar flow, n equals to 1. Now, for turbulent flow, what will you get? Turbulent flow, n equals to, generally for Bloch's type of equation, if we use Bloch's type of equation, if we use, then this n equals to usually 1/4, is not it? So, if you substitute that, then in that case we find that in this particular case, if you just do it, we just calculate 1 by phi L square whole to the power 4 by 7 plus 1 by phi g square whole to the power 4 by 7. So, that we can have a 1 at the end, just for that reason. If you just calculate it and you can find out what is the thing that you are getting, this will become 1 by, suppose in this particular case we know 1 by phi L square was 1 by 1 minus x whole to the power n 1/4 minus 2, is not it, plus 1 by x to the power 1/4 minus 2. So, in that case you do, it is going to be 7 by 4, 7 by 4. So, therefore, this becomes equal to 1. So, now is it clear what are the limiting conditions to which the relation between phi L square and phi g square they confer to? The limiting conditions are, in a nutshell, if I write down the limiting conditions, for no gas flow 1 by phi L square equals to 1 and 1 by phi g square equals to 0. Confusions remaining now also? Just do the derivation. Okay. See, these are small derivations, these have come just from single phase fluid flow. Okay. There is nothing two phase in this, but please remember, whenever you are doing any derivation for your exams or something, please remember that start from the very basics, start from the definitions, and then we are going to proceed. This remember. So, in a nutshell, what are the limiting conditions of the correlation? For no gas flow, 1 by phi L square equals to 1, 1 by phi g square equals to 0. For no liquid flow, 1 by phi g square equals to 1 and 1 by phi L square equals to 0. And at the critical point, we have two different relationships depending upon whether the two phases are in laminar flow or in turbulent flow. For laminar flow, as it is very evident, it is 1 by phi L square plus 1 by phi g square equals to 1. For turbulent flow, assuming a Bloch's type of relationship, we get 1 by phi L square to the power 4 by 7 plus 1 by phi g square to the power 4 by 7 equals to 1. So, remember one thing, we have started deriving the relationships between the two phases. Yeah, these things more or less has been covered. So, therefore, we have started deriving the relationships between the two phases between phi L square and phi g square, just because we know that from the very beginning both the phases are going to be present, and phi L square and phi g square, they conform to certain limiting conditions to which phi L square and phi g square do not conform. Okay? And the limiting conditions are as we have derived. Now, so therefore, based on these facts, what have been done? The certain empirical correlations have been proposed. Now, these empirical correlations, they have related phi L square and phi g square based on certain assumptions. What are the assumptions that I have already mentioned? The first assumption is that the flow occurs, or the empirical correlations have been derived for circumstances of isothermal two component flows where in horizontal pipes, or in other words, to be more explicit, the correlations have been derived for conditions where negligible body forces are there are no acceleration pressure gradient or no phase change, and more or less the total pressure gradient comprises of the frictional component only. Under that circumstances, these derivations have been derived. Now, the oldest derivation or the most widely used derivation which was derived, or which was the first, almost the first derivation which was derived in this regard, was made by a group of workers commonly known as the Martinelli and Nelson co-workers, or the Lockhart and Martinelli. These two persons, they first derived the empirical correlations, and subsequently there were several other modifications of these correlations, but the basic form has remained. So, we will be discussing the Lockhart and Martinelli correlation first, and then we will be discussing the modifications which has been suggested to expand the range of applicability of these correlations. Now, this Lockhart and Martinelli correlation, it was derived on the basis of certain assumptions. What were the assumptions? The assumptions were, some assumptions are justified, some are not. The first assumption is that the two phases, they flow in two separate cylinders. That is quite justified, that they do not intrude into one another. Okay? And therefore, the cross sectional area of the two cylinders is equal to the pipe cross section. This was the first assumption. It was first assumed that both the phases, they flow in separate cylinders, such that the cross sectional area of cylinder 1 A1 plus the cross sectional area of cylinder B, cylinder 2 or cylinder B A2, they add up to give you the total cross sectional area of the pipe. So, mathematically the first assumption is A1 plus A2 equals to A. What is the next assumption? Come to assumption 3. The pressure drop in each imagined cylinder is same as in actual flow. It is quite natural. Okay. So, the thing is, it is sort of, if you imagine, it is something of this sort. We have a pipe where more or less fluid 2 is flowing here, fluid 1 is flowing here. We assume that more or less they are flowing in two separate cylinders, such that the cross sectional area of this and the cross sectional area of this, they add up to form the total cross sectional area of the pipe, which is nothing but pi by 4 d square. Okay. The next assumption is they do not interact at the interface. If they do not interact at the interface, that means they are flowing irrespective of the presence of the other, they do not know that the other fluid is present. Under that condition, the pressure drop across the cylinder 2 will be equal to the pressure drop across the cylinder 1, which will be equal to the pressure drop across the total conduit. Yes or no? It is just like a parallel connection, the voltages are the same. This is just the same thing. So, therefore, we find that if you consider the second assumption, the two phases do not interact with each other, then we find under that condition the pressure drop or the pressure gradient across the entire cylinder, this will be equal to the pressure drop across the cylinder, the liquid cylinder if we say, or the cylinder 1, this will be equal to the pressure drop across the gas portion. So, let us see, remember one thing, we had already defined phi L square and phi g square, lot of definitions are coming into picture. If you remember, this L was when liquid was flowing alone in the pipe. Okay. This was when gas alone was flowing in the pipe. Okay. Now, when we are defining this, this is the liquid portion when both the phases are flowing together. So, definitely the cross sectional area occupied in this case will not be equal as the cross sectional occupied when the liquid portion is flowing alone in the pipe. Do you get it? So, therefore, this dP dz L and this dP dz L, this cannot be the same. So, therefore, we have to remember it and we have to denote this with a different nomenclature. We will just put it liquid portion, okay, gas portion. Whatever you want, you can use your own nomenclature, it does not matter, but you have to remember one thing, that here for what is the assumption that I have written? The assumption is pressure drop in each imagined cylinder is the same as in actual flow. So, therefore, here the pressure drop refers to the pressure drop across the liquid cylinder, in this case it is across the gas cylinder. Okay. And the pressure gradients which I had defined for the two phase multipliers, they refer to the pressure drop which would be encountered when the liquid which is flowing here only in this portion now flows through the whole pipe. Is it clear? Since they are occupying different cross sectional areas, naturally the friction factor, everything, the total, everything is going to change, and therefore, this particular pressure drop and this particular pressure drop are going to be completely different. This part you are supposed to remember. Okay. So, therefore, there is a need. So, since we will be dealing with this much more, so when liquid or gas flows alone in the pipe, they will be denoted by a subscript capital L or capital G. Okay. And when it is the liquid portion which is flowing, then we are going to put it either a liquid portion or a liquid cylinder, whatever it is. Okay. So, this is the third assumption which we are going to give. And the fourth assumption which you already know, we assume that the pressure drop is mainly due to frictional component, which I have also put down in my PPT. Okay. In the PPT also this has been put down. So, therefore, the fourth assumption which has been put down in my transparency or in my slide which I have prepared. So, this is minus dP dz, this primarily comprises of the frictional pressure gradient. Is it clear? Are these two assumptions clear? The first assumption was fine, it is assumed to flow in two separate cylinders where the two cross sectional areas add up to form the total cross sectional area of the pipe. Second assumption is the two phases do not interact with one another. Remember one thing, this is the most severe assumption, and we will see at one point why that it does not give you completely accurate results. The primary reason is the assumption 2 which I have put down in my transparency. Okay. In the transparency or in my projector, the second assumption which I have put down, which tells you that the frictional pressure, the two phases do not interact with one another. If they do not interact, then naturally it is not two phase flow at all, because in the first class the definition which I had given you about two phase flow is, it is the interacting flow of two phases. So, therefore, remember one thing, if that assumption is not valid, then there is no point. So, therefore, this is the most severe assumption, and we will see that for this particular assumption it does not give you completely accurate results, but for the time being, since the relationships will be derived based on certain curve fitting of experimental data, large number of data. So, more or less the relationships which we get are accurate. Okay. So, the next assumption is the two phases do not interact with one another. Now, moment this particular assumption comes into picture, so naturally what happens, the pressure gradient across the liquid portion or across the liquid cylinder will be equal to the pressure gradient across the gas cylinder, and that will be equal to the pressure gradient across the two phase flow or across the mixture, across the composite gas liquid cylinders, is not it. So, therefore, the second assumption which I have written down, this is nothing but, if you take the transparency, you are going to see the second assumption is that the total pressure gradient, it is equal to the pressure gradient in each imagined cylinder. Okay. So, the third assumption is basically nothing but it is an extension of the second assumption. So, the next assumption is the pressure drop arises mainly due to frictional component. How did this assumption come up? Because these correlations were derived for two component flows, they were derived for air water mixtures in horizontal pipes. So, therefore, in horizontal pipes means there was no gravitational component, two component air water mixture means there was no phase change. So, there was no acceleration pressure gradient and they were in circular pipes. So, there was no area change as well. Okay. So, therefore, the pressure drop is mainly due to frictional component, or in other words minus dP dz Tp, as I have written it down, this will be equal to minus dP dz, the frictional component of the two phase mixture. Fine. Now, from this particular assumption and this particular assumption, what do we get? From these two assumptions we get, so therefore, minus dP dz two phase, this is nothing but the frictional component of the two phase pressure gradient, which is nothing but the frictional component in the liquid portion, which will be equal to the frictional component in the gas portion. Okay. So, this is the finally this is the final expression if we couple up all the assumptions which we have. So, finally, the assumption 1 is this, assumption 2 is A1 or AL plus AG equals to A. And what is the next assumption? Now, so therefore, in order to find out or rather how to find out your frictional pressure gradient, we assume that this frictional pressure gradient can be obtained if we know the frictional pressure gradient in the liquid portion. Now, in the liquid portion it is simply single phase liquid flowing through the pipe. Okay. So, therefore, this can be obtained from single phase flow equations. This can also be obtained from single phase flow equations, is not it. So, therefore, under these two conditions what happens, my phi L square, this was originally this was minus dP dz Tp, if you remember, by minus dP dz liquid, right. Now, this becomes minus dP dz frictional Tp, fine, or let me write it, sorry, Tp by minus dP dz, your frictional part of the liquid, because for liquid there is no acceleration, it is a horizontal pipe. So, all those assumptions are applicable, or in other words this is nothing but equal to minus dP dz frictional of the liquid portion divided by minus dP dz frictional when the same liquid flows alone in the pipe. Could you get the thing, the simplification which has been reduced in this particular portion? Now, we will see that same liquid is flowing, here it is flowing through some portion of the pipe, here it is flowing through the entire portion of the pipe, yet these two pressure gradients are not equal. Do you understand? As a result of the assumptions which I had written down in my transparency as well as here, as a result of these assumptions, what have I arrived at? I have arrived at finally as a result of this from the Lockhart and Martinelli correlation. Just remember the first group which had given the correlation, it is the Lockhart and Martinelli correlation, or this is usually told as the separate cylinder model. This is also known as the separate cylinder model. Okay. So, therefore, from this model we get phi L square is nothing but minus dP dz frictional liquid portion of the pipe divided by minus dP dz frictional when that liquid flows alone in the pipe. Similarly, phi g square, this will be minus dP dz. You can take frictional gas flowing alone. See, gas portion and liquid portion, they are the equal, is not it? F gas portion and F liquid portion is equal, which I have already shown you here. Minus dP dz two phase minus dP dz frictional component is the frictional component in the liquid portion, frictional component in the gas portion. Okay. So, therefore, this therefore becomes by minus dP dz frictional when the gas flows alone in the pipe. Agreed? So, therefore, what basically they did, the Lockhart and Martinelli, they proposed a correlation based on the separate cylinder model, where they tried to correlate these two parameters phi L square and phi g square. Okay. More or less the graphical correlation is, if you see here, the graphical correlation is something of this sort. They have tried to correlate 1 by phi g square and 1 by phi L square. We will be discussing this graphical correlation, and then we will find that just very simple, by some very simple analysis we can find out the analytical expression for the family of curves which I have shown here. So, basically Lockhart and Martinelli, they stopped by proposing this graphical correlation, and then subsequently other co-workers Martinelli, Nelson, etc., they proposed the analytical correlation simply by substituting minus dP dz F liquid portion minus dP dz F when liquid flows alone in the pipe, by simply substituting these expressions correctly from single phase flow equations. They could arrive at a analytical expression relating phi L square and phi g square, and as is evident, you can very well understand that this relation will again depend upon whether the two fluids are flowing in laminar flow, turbulent flow, or whatever it is. Okay. So, tomorrow we will be continuing our discussions regarding the Lockhart-Martinelli correlation, and then if time permits, we will be going to the other modifications of the correlation. Thank you very much.